Thanks for joining today's session. In the next 30 minutes, I'm going to introduce our latest steps of running vLLM on Intel GPU, Intel Gaudi, and the Intel data center CPUs. So there will be 3 topics we cover in today's session, including serving vLLM on Intel platform, inference at scale, and inference with quantization. So first of all, I want to say that Intel treats vLLM as the most important production serving framework. Intel have dedicated team working on vLLM in daily basis for Intel GPU, Intel CPU, and Intel Gaudi enabling. Meanwhile, Intel is also the top-ranked contributor to PyTorch ecosystem to support Intel GPU and Intel CPU. Intel Gaudi is enabled with PyTorch as extension through the Habana Synapse software suite released by us. So what does Intel contribute to the vLLM? You probably ask. I want to use this diagram to show the commits we've been contributing to the vLLM over the last 2 years. From the right side, you can see that I counted commits by organizations, and Intel contribution is ranked as top 10 among all, right after Hugging Face. From the left side, I categorized our commits into different types. So the top 3 categories are enabling Intel CPU, GPU, Intel Gaudi. However, we also contribute common features such as PD disaggregation, quantization, and the modeling support into the vLLM. Moreover, we also, besides the vLLM main repo contribution, we also have 2 other projects under vLLM project namespace, which are vLLM Gaudi plugin and the vLLM XPU kernels. Okay, now I want to give you a very brief introduction of how vLLM working with all different platforms. From the left side, you can see the major components of vLLM are scheduler, worker model runner, model executor, and the distributed utils underneath. The scheduler, engine core, modeling, and the quantization method, also KV connectors, are shared with all platforms in a more hardware agnostic way. And what model runner, OP implementation, attention kernels are more platform specific. So what does that mean? That means that Intel needs to provide our own flash attention kernels, share the same API as CUDA, and the vLLM is able to dispatch attention abstractions to Intel GPU flash attention kernels. On the right side, I use a different way to show how we support in vLLM stack. So I use different color. Gray means common features, common components, and dark blue and the light blue means platform specific and plugins. So our work has mainly focused on the dark blue and the light blue boxes in vLLM. Okay, so what does that mean? So far, I want to list all the status of vLLM on all our 3 platforms. Left side is feature status, and right side is model status. I want to start with the Intel Gaudi. So Intel Gaudi supports all major features in vLLM, including eager mode, graph mode, and the torch compile mode. Data parallelism for MLA, expert parallelism for MOE are also supported. PD disaggregation through Nixel is well supported as well. And the only partially done feature is spectral decoding. We only support single draft token at this moment for Eagle 3 and MTP. Multi-token drafting is planned for next release. For modeling support, Gaudi support multi-model models such as Llama 4, Scout, and Maverick, Qwen 2.5, VL, and the Gamma 3. And for large models such as DeepSeek R1, it's also supported natively on Gaudi by the native block FP8 quantization format. Currently, we are still actively working on to support GPT-OSS. Should be ready in the next release as well. So for Intel GPU, we are currently running Intel GPU with our BattleMage B60, which support major features such as eager mode, PyTorch compile mode, and the PD disaggregation. Also want to mention that Triton kernels are natively run on our Intel GPU as well. But for the graph mode, it's still work in progress, as well as multimodal spectral decoding. And those features are expected to be done by end of this year. For modeling support, because of the current device memory, it's only like 24 gigabytes for this generation, so we didn't validate large models such as Llama 4 Maverick or DeepSeek R1. But we already support GPT-OSS 20 gigabytes and 120 gigabytes models on B60. For CPU, we don't support graph mode, and the rest of the missing features such as spectral decoding and the PD disaggregation are work in progress. And for modeling support, usually expect to run CPU with smaller models such as 1B, 3B, and the 8 billion model, and we will show the data in the later pages. Okay, so in the next 3 pages, I want to share the current status for Intel CPU, GPU, and Intel Gaudi. For Intel CPU, we're offering 3 generations: Sapphire Rapids, Emerald Rapids, and Granite Rapids. Granite Rapids is our 6th generation, which is our latest offering from last year, which with 128 physical cores, and both option for DDR5 and the multiplex rank DIMM memory option. Performance-wisely, we provide 2 data points here. The above one is from the public blog, and the bottom one is from the MLPerf 5.1 submission. From the above blog, we are comparing vLLM 0.9.1, which I think it's like around September release, with Intel Granite Rapids versus AMD Turin EPYC 9755 and 9965. We can see that Intel Granite Rapids is around 1.4 better in throughput comparing to 9755. If you look at the green column comparing to the dark gray column. And it's also around 2.7x better than 9965. So the data is measured by 128 input token and 256 output token. With larger input and output tokens, such as 1K, 1K, we still see 2 times better comparing to 9965. The second table is showing the number we submitted for MLPerf 5.1 submission. So the data here is showing that we are running the CPU Llama 3.1 8 billion model in both offline mode and serving mode on a single node Granite Rapids, and the offline inference on Whisper model. So you can see that actually the offline throughput is pretty good. But the online, the online serving mode is not that good because we have the SLA limitation, which is 1 second for TTFT and 100 milliseconds for TPOT. By the way, for more data, you can just go to the vLLM PyTorch benchmark dashboard. We are now providing live performance for CPU. Okay, for GPU, we have 2 offerings. Intel Arc Pro B60 is available at this moment with 24 gigabytes device memory and 20 XC cores. And the Crest Island is our next offering as a data center GPU with 160 gigabytes device memory and native MX FP4 support, which will be available next year. From the right side, I also provide 2 data points. One is from the blog we are releasing on vLLM shortly, and showing the throughput of serving distilled Llama 8 billion, Qwen 40 billion, and Llama 70 billion with 8 cards of B60 with a SLA limitation. And the bottom one is also from the submission for MLPerf 5.1, showing the throughput per dollar comparing to NVIDIA RTX Pro 6000 and L40S. And you can see that the Intel Arc Pro B60 performance per dollar, advantages of up to 1.25 times and to RTS Pro 6000 and 4 times better to L40S respectively. Then we talk about Gaudi. So Gaudi is comparing to NVIDIA H100 and 200. We have two products for Gaudi, Gaudi 2 and the Gaudi 3. Gaudi 3 comes with 128 device memory on each card. So from the right side, the above data is from a public blog from Dell Technologies released around May, and they tested vLLM on Intel Gaudi 3 comparing to H200, respectively. With the use case of input token is 128 tokens and output is 128, actually you can see the throughput, raw throughput comparing between Gaudi 3 and H200. Gaudi 3 is around 1.27 times better. So the way to look at it is like the start of the orange line comparing to the end of the orange line, because the middle is using B200, so which we are not be able to compare to. And for the throughput per dollar, which is looking at the blue column comparing to the green column, and the Gaudi 3 is 1.65 times better comparing to B200, and the 3.27 times better comparing to H200. Oh, sorry. And the bottom data is from the vLLM PyTorch dashboard, benchmark Llama 3.1, 8 billion, 17 billion, and the Mistral 8 multiply 7 billion model with shared GPT data. From the throughput data, you can see that the Gaudi 3 is with higher throughput to H100. The way it's like just looking the blue line comparing to the green line. And the throughput per dollar, Gaudi 3 is providing a better TCO, ranging more than 3 times better to H100. Okay, so now I want to talk about inference with scale. So when we want to talk about inference with scale, the use case is PD disaggregation. Early this year, Intel AI Group leader Sachin published a joint paper with Stanford University Gimlet Lab proposing a blueprint for heterogeneous arc for PD disaggregation. That the customer can continue using their CUDA, which is H200 or B200, to serve the prefill and for all the compute-intensive model forwarding and leveraging Gaudi 3 to serve decoding for memory-intensive model forwarding. If you already visit our Intel booth, you should also see the TCO benefit written in the booth. And here I want to discuss all the tech details we need to resolve to support such heterogeneous arc design. So for the software stack, we are using LMD routing strategy as a top layer to routing all the user requests to different nodes. In the vLLM, we leverage NIXO connector to transfer KV cache in a per request granularity. So prefix cache is also supported here because it's already fetched per request, and we don't need to transfer all the cached prefills. And for NIXO, we are providing our Intel staging NIXO implementation with Intel staging UCX to enable CUDA to Gaudi device direct transfer over the RDMA. So now let's see all the implementation details for vLLM side. So there are 4 major challenges we need to conquer for supporting this heterogeneous arc. So first one will be there's no such a backend which is a GPU to Gaudi direct, right? So this is something we need to enable. And secondly, we need to support heterogeneous KV layout, which is that, so usually the KV will have two type of layout, which is the KV number head as outer dimension or the block size is out of dimension. So this is a second challenge we need to handle. The third one is that with the heterogeneous tensor parallelism, which is like using only TP1 for prefill and the TP2 or TP4 for decoding, then we also need to handle that with heterogeneous KV layout. The fourth one is heterogeneous block size. So let's talk about the first one. Nowadays in vLLM, Nixel connectors support two types of KV transfer. The first one is to utilize the host buffer. The second one is doing the device direct. So through the host buffer, it's very simple, which means that you will have allocate a same size of KV cache on your CPU. And every time when the KV cache gets updated on the device, data will be synced to the CPU buffer per request in a synchronized way. And the Nixel transfer is basically copy the CPU tensor to another remote CPU tensor using the IBverb backend. So in such an implementation, a lot of problem will be easier for the heterogeneous because we can always do the KV layout permute or block size shuffling during the copy from host to device. But the only downside of such implementation is that when you have an extremely large KV cache, let's say, think about like doing, 256 batch size for DeepSeek, and then you will have so many data to copy, and the copy time from host to device or device to host will be very slow. So the second option will be transferring through the device direct, which will be a better option for performance perspective. However, the problem there is that if we are doing that, then it will be not like single line from device to CPU and transfer to another node. It will be like multiple lines across different type of devices. So we need to implement like CUDA to Gaudi device direct and also like following options in the future to support such a heterogeneous arc. The second problem for using device direct will be the block size shuffling. So in the second diagram, I provide a simple flow to show what is this type of problem. If you're familiar with what is block size, which is like how many tokens will be in the single block, right? So usually for CUDA, the block size is 16, and in Gaudi, we are using 128 because it's better for the gen. And in the diagram, I use a simpler case, which is block size is 4 for prefill, and the block size is 16 for decode. So if we are doing this heterogeneous block size transfer, which means that the first 4 tokens need to be from head 0, 1, 2, 3, need to be copied to the different region in the decode side. So which also means like we need to gather 4 blocks from the prefill to complete the 1 block in the decode side. So this problem we are actively working with vLLM community to resolve, and the PR is already submitted, and so pending for the final review. So with all features enabled on vLLM, we also need to support LMD for Intel GPU and Intel Gaudi enabling. Currently, Intel GPU is supported in LMD, and the Intel Gaudi PR is pending on review. Also, we have our Intel Kubernetes team to support us for device plugin enabling for Intel GPU and the Intel Gaudi. Both device plugins are enabled and well maintained. In the next step, once all the vLLM features and the LMD platform support are enabled, we will be able to validate all the features from LMD to understand the feature gap and also doing some common feature contribution to the LMD. And another plan is that we also want to proposing this new routing grading strategy to further improve the cost efficiency for heterogeneous arc into the smart routing strategy of the LMD. Okay, so the last part, I also want to talk about the quantization. So from the left side, I want to summarize the current status of supporting quantization with all three platforms of out-of-box quantized models. So Gaudi shows a better coverage for native FP8 on both per-channel quantization and per-block quantization. And the Gaudi also supports compressed tensor format, which is a very important data format in vLLM, which is contributed by Red Hat LLM compressor team. For GPU, currently we does not support compressed tensor, but we support native FP8 and MX FP4. And for Intel CPU, we only support W8A8 and the Inter4 with AWQ and the GPTQ. On the right side, I also want to show the very latest data for running GPT-OSS MX-FP4 model on Intel Arc Pro B60. So the raw data here is showing the throughput on 20 billion model with single card at 120 billion model of 4 cards. So you can see the data is not bad. Besides for supporting all the essential quant method in vLLM, Intel is also contributing for integrating innovative quant method. So in the last quarter, Intel contributes this auto-run algorithm into the vLLM, which achieves a very high accuracy for 4-bit. So look at the right bottom chart. The purple column is with auto-run on 4-bit, and the green column is with 16-bit. So you can see the purple column is very, very close to the 16-bit and are way better than the rest of the 4-bit algorithms. On the top, I also show an overview of the algorithm, but I won't be able to explain the detail. If you are interested, please check on our vLLM auto-run intro page, which is on the vLLM website. Auto-run is now working in progress to integrate into LLM compressor and to support natively for compressed tensor in the future. OK, time for wrap up. So what is a key takeaway? Firstly, I want to say again that Intel is devoting on supporting vLLM and PyTorch on all Intel platforms. For CPU, we are aiming for inference and embedding with small language models, but delivering the reasonable SLA for online serving. For Intel GPU, we are showing strong TCO advantages at MLPerf 5.1 comparing to L40S and RTX Pro 6000. And the Intel GPU is preparing vLLM for next generation Intel data center GPU, which with 160 gigabytes device memory. And for Intel Gaudi, we are delivering competitive SLA to H200, which much lower cost. And we are able to serving very large language models, over 400 billion in BF16 and 800 billion in FP8. OK, so try it today. So I'm providing 3 GitHub. The Intel GPU and the Intel CPU are in the main project, vLLM project, and the Intel Gaudi is provided as a plugin, which is under the vLLM project, vLLM Gaudi. And we are also providing all the XPU kernels under the vLLM project, vLLM XPU kernels. And I'm also providing all the Docker run command. You can see it's very easy to start your service.
Thank you, Chendi. Are there any questions from the audience?
Yes.
For the SLM, for the CPU, Intel CPU, for the SLM, what's the size that you support the parameters?
Yeah, so we can support like 8 billion model. You can check on the performance on the vLLM dashboard. The data, you can just see the latest data. It's live dashboard. You can check on every day.
Could you say more about the cost-aware routing?
Oh, sorry.
You had a slide that talked about cost-aware routing. Can you explain more about what that is?
Cost of the routing.
Cost-aware.
Oh, cost aware. Yeah, this is just a plan. We haven't to start work on that yet.
Mm-hmm. Okay.
Yeah.
Are you guys working with Microsoft on the semantic kernel?
Do we work with Microsoft?
So we have some discussion with them, but like because it's with different language, or haven't started any concrete work yet. But I'm not sure where are you from, Microsoft? Oh, okay. Yeah. Otherwise, I'm happy to follow up with them for like any possible collaborations. Yeah.
By the way, this is Ding Ke from Intel. Okay, if there's no more questions, please give another round of applause.